equal to f of x is twice differentiable such that f of a is equal to f of b equal to 0 and f of x is greater than 0 for all x belonging to the open interval between a and b. Prove that f double dash c is less than 0 for some c belonging to the open interval a and b. How do you proceed in such a problem? Clearly, there exists a double dash and you are given certain conditions for f of x. So we'll go on to the mean value theorem, and probably we'll have to apply the mean value theorem twice, given that it is f double dash x we are dealing with and not f dash x. So how do you go about it? First, split the interval into two different parts, the easiest being of course split it at a plus b by 2. Apply the Lagrange's mean value theorem to the interval a comma a plus b by 2, the open interval of course. And you can always find an alpha such that f prime of alpha equals f evaluated at a plus b by 2 minus f evaluated at a upon a plus b by 2 minus a. This gives you 2f a plus b by 2 upon b minus a is greater than 0. Similarly, apply the Lagrange's mean value theorem in the other interval, that is a plus b by 2 comma b, and you get a certain beta. Now apply the Lagrange's mean value theorem to alpha comma beta. Why? Again I remind you, because we have an f double dash c term to take care of. So when you apply the Lagrange's mean value theorem in the interval alpha comma beta, you have f double dash evaluated at some point c equaling f prime beta minus f prime alpha upon beta minus alpha, which is equal to minus 4 into f evaluated at a plus b by 2 upon b minus a into b minus alpha. Clearly b is greater than a, and clearly since beta was evaluated in the latter interval and alpha in the former interval, beta exceeds alpha. Now f of x has been given to be greater than 0. So again, minus f minus 4 into f at a plus b by 2 upon b minus a into beta minus alpha is definitely less than 0. Let's move on to a question from probability. There are 4 balls of unknown colors in a bag. A ball is drawn at random twice with replacement and found to be red. The contents of the bag are replenished. Now if the 2 balls are drawn simultaneously from the bag, find the probability that both the balls are red and assume all numbers of red balls in the bag to be equilikely. In probability, the most important step is to define and list out each and every event possible. So how do we go about this? Let Bn be the event that the bag contains n red balls. Since all cases are equilikely, probability of B of n, since all cases are equilikely, probability of Bn equals 1 by 5 for n equal to 0, 1, 2, 3 and 4. Now let A be the event that 2 balls are drawn one by one with replacement and both of them are red. Then we have probability of A given B0 equal to 0, probability of A given B1 equal to 1 by 4 into 1 by 4, which equals 1 by 16, and so on. Let Bn prime be the probability that the bag contains n red balls, given that A has occurred. So we have probability of Bn prime equals P of Bn given A, which equals P of Bn into P of A given Bn upon P of B1 into P of A given B1 plus P of B2 into P of A given B2, and so on by Bayes' theorem. Since P of Bn equals 1 by 5, they cancel out and we get P of Bn prime equals P of A given Bn upon P of A given B0 plus P of A given B1, and so on. On solving this, we obtain P of B0 prime equal to 0, P of B1 prime equal to 1 by 30, and so on. Now, Let X be the event that two balls are drawn simultaneously and both of these drawn balls are red. Then P of X equals P of X intersection B0 prime plus P of S X intersection B1 prime plus so on. Since B0 prime, B1 prime and so on form an exclusive and exhaustive set of events, this expression is definitely valid. Now, P of X intersection Bn prime equals P of Bn prime into P of X given Bn prime. Therefore, we finally have P of X equals 0 into 0 plus 0 into 1 by 30 plus 4 by 30 into 3c2 upon 4c2 plus and so on. Therefore, we have P of X equals 0 into 0 plus 0 into 1 by 30 plus so on, giving us the final answer. Let's go on to another illustration. We are required to evaluate the integral dx upon a plus b cos x whole square, where we are given that a is greater than b. Now, in such a question, quite often the first strategy that a student employs is to attack the problem by converting the cos into secant x and then going on and doing some juggling with the problem. In this case, with a very preliminary juggling, you can realize that that strategy does not work. So what do? We consider something else, something rather out of the box. Now take this new function. For example, first look at cos of x. Clearly the derivative of cos of x is minus sin of x dx and the integral is sin of x. So how do you go about this problem? Take a new function sin x upon a plus b cos x and take the derivative of this function. Why do we take the derivative of this function? Because we want a plus b cos x whole square in our denominator. So derivative of sin x upon a plus b cos x equals a plus b cos x into cos x plus b sin square x upon a plus b cos x whole square, which comes out to a cos x plus b upon a plus b cos x whole square, which implies that sin x upon a plus b cos x equals integral of a cos x plus b upon a plus b cos x whole square dx. Now let our integral, the one we were supposed to evaluate at the outset of the problem, let that integral equal I. So sin x upon a plus b cos x equals bi plus integral of a cos x dx upon a plus b cos x whole square. This equals bi plus integral a upon b into b cos x plus a minus a upon a plus b cos x whole square dx. This gives us bi plus a square upon b into I plus a upon b integral of dx upon a plus b cos x. This last integral is a relatively simple one which can be evaluated by putting cos of x in terms of tan square x, from where on you have the answer. So what should be a final revision strategy for the mathematics portion of the joint entrance exam, especially in the last 3 months leading up to your exam? First of all, a proper planning of your revision is necessary.